Greetings, my inductive friends. Zooming into the weekend here soon. Our last weekend with instruction, and then next weekend is your first weekend before finals. Well, it's the weekend right before finals. There are lots of weekends before finals. Well, anyways, so this is kind of our end of our second to last week. Coming up pretty soon here. So let's get to a little bit more of induction. So what I wanted to do was start with this example since we did the sliding rod example last time. Here's an example of a rotating loop in a magnetic field. So what's happening is, for example, maybe you have this loop on bearings or something like that on the up and down side of it, and it spins about that axle. So that if you looked, say, if you looked at it from above and then kind of turned so that I was looking at the B field that looked like, say, this. Let's go like this. Okay, so this is a view from the top and rotated 90 degrees. Okay, so it's like you go look at it and then turn this way. Okay, so now this is what the B field looks like. Okay. Oops, a little hitch in that one. Okay, so that's about all we need here. So if you're looking at the loop to start with, we can say time t equals 0, say, okay? And now the loop is here. All right, so this is time t equals 0. And at this point, I think you can see the flux is going to be a maximum through this loop, okay? The flux through the loop is maximum. I'll actually make the loop a little bit bigger so I can catch these outside ones here. There we go. Okay, so the flux is a maximum right now because the arbitrarily, I guess, we can consider the little n hat vector to be pointing normal to the, all right, we can consider the area vector, the little unit normal, right, is pointed perpendicular to the area. So arbitrarily, we can consider that to be our starting point, and that is lined up with the field. So then what's going to happen if I'm looking down like that? The next thing it's going to do is it's kind of going to rotate. If I'm looking down on it this way, and the B field is that way, and I'm rotating that thing counterclockwise. So the next thing I'm going to do is I'm going to see it kind of like that. So the next thing is going to be something like this. It's going to rotate around like that. Okay, and it's going to rotate towards the position like this. And then it's going to rotate this way. And then it's going to be back to here, at which point the normal vector is now that way. So that's your half turn. Oops, that's supposed to be an n hat there. That didn't really work out. Let's try again. Okay, so that's your half turn, and then it essentially goes through and does that again, right? So it's gone from here, it's gone there, there, and here, and now it's going to go back to doing that again. So maybe I can squish these in right here, but it's going to do it again with essentially the unit vector pointed the other way. Whoa, okay. Okay, but anyways, the point being here that we're going to concentrate on let's just take a look at the first half turn here. The flux at t equals 0 is a maximum. maximum flux. Okay. Now the flux is less. Lower flux. And then by the time you get, and so that's this one. And then by the time you get to this one, can you see that there's zero flux? Then you're back to lower. Well, you're back to something that's intermediate, maybe, I guess, is a better way to think about it. In between. And then back here, you're back again to a maximum valued flux, although it's going to be a negative, right? The flux now is, since the B field is to the right and the normal vector is to the left, I'm going to get a cosine of pi, which is going to throw me a -1 in here. However, the magnitude of the flux is maximal at these points. So I'll say this is max. So I could change this one over here. The first one I can change to put a positive sign, max positive flux. This will be the max negative flux, like so. And then the whole thing repeats itself. So if we were to try and graph what the flux looked like, what the flux does the flux look like? Okay, so here is the symbol for flux. It's capital Phi, big I with a circle through it. Because we have fluxes for both, I'm going to label that the B flux. And here's the time axis here. So at the start of this thing, I'm going to start with a maximum positive flux here. So we'll call that right here. There it is. And then it's going to be lowering down to some value like there. And now it's 0 at this point. And then by the time I get down here, now it's got to be, you see at the first instant of intermediate, see the normal vector would be pointing kind of up that way, and that would give you a positive. Now it's going kind of back that way, which means it's slightly on the negative. So it's coming down through here, and then your max negative flux, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 is right here. Something like that. Okay. So what this ends up looking like is the first part of a cosine, right? If I extended this down, if I extended the axis, you'd find, whoops, you'd find, well, because I had to kind of squish those in right there. So I'm trying to match the top pieces to the graph here. So I squished it all in here. But if I was doing this properly, then oops, a bit big there. I think you get the idea. Like something like that. So it would be a cosine. The flux therefore looks like a cos, and that comes out from basically thinking about the dot product between the n hat and the field. So if I take a look at the flux, let's see if we can see this mathematically. B dot dA through this surface. Okay. B is a constant, so out it comes. But now it's the integral, but the dot product, right? The dot product of n hat with dA, or not n hat with B, the dot product of these things is going to force a cosine in here, right? So what I'm going to get is I'm going to get the area, but then the area of the loop, but then I'm going to get the cosine of the angle in there from the dot product. And if it's rotating, then that becomes something like an omega times a delta t for the interval, right? So that's like a displaced angle. Now, what the question is what's the EMF generated in this loop? So the EMF is minus d by dt of the flux. Okay. And so looking at the cosine function here, what I'm going to get is I'm going to have to do a derivative of b times a times cos theta. Oops, except it's not cos theta anymore. It's going to be cos omega delta t. Okay, like so. Oh, you know what? Now think about this though. If we had multiple windings, we should let me go back and do that. What if I have multiple windings around my loop? Well, then the flux is going through every single loop. So I count up each loop. There's a flux here and a flux here and a flux here. What if my loop has a bunch of turns? What if it's a 10-turn loop? With n turns, the flux becomes NBA cos omega t. Okay. Because it just becomes multiplicative. So let me just put that n in right there. So now it becomes that. So the d by dt combs through, finds the cosine, and says, okay, I've got to take a minus NBA. I got to take an omega out here. I'm going to change the cosine. The derivative of cosine would be negative of the sine. So these two minuses are just going to go away. And the EMF is going to be NBA omega sine omega t, like that, so that when I look at the graph of it, now I'm going to say, all right, well, this is the derivative of the flux. So I'm looking at the slope of the flux to know whether or not I'm getting a generated EMF in the loop. Right at the very top, you can see the slope is 0 here. And that's why I'm starting off with a sine, because the sine starts at 0. By the time I get to here, this is as I go down through the quarter cycle, right? It's tipping, 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 and it reaches its maximum slope right as it goes through the 0 point of flux. So right at this point, I should be generating maximum EMF in the loop, like that. And then it's going to go down, and by the time I get down to here at the lower extreme of flux, I'm going to be back to 0 again. And it's going to repeat like that, although, did that work out okay? Oh yeah, that worked out pretty well. Kind of, well, close. All right, so if I go back up here and I realize that the maximum EMF generated is when the loop, what just happened here? Oh man. Okay, so that makes no sense at all. If I realize that the EMF, the maximum EMF generated, it happens when the flux is 0. I'm going to go back over here and I'm going to say, look, I got maximum flux. E equals 0 here. E is a maximum here. E is 0 here. Okay, so this is called a phase difference. Okay, this is called two waves being out of phase by 90 degrees. Okay, in fact, you would say that if I thought about the flux relationship with the voltage, with the induced EMF here, you'd say that the flux actually leads the voltage, because the flux starts at a peak and then a little bit later in time, the peak happens for the EMF. So the flux is actually leading. It peaks first in time, right? Because it starts at a peak, and then a quarter cycle later, that's when the EMF peaks. Okay, so that's a little funny, isn't it? But that's an interesting little side note. You call the flux in this case leads the EMF, and it does so by 90 degrees the quarter cycle. Okay, just simply because the peak hits first. The flux peak hits first, then the EMF peak hits a little bit later. Okay. All right, so there's that. And I just went and found a few numbers here, and I thought it might be interesting to see if we take the generated EMF here, and we say, okay, I'm going to take that, and just as a number example, just because it's here, we have Moss Landing. And if you go to the Moss Landing website, they have a power plant there. You go to that website. I mean, when I say Moss Landing, I'm sure there are many things in Moss Landing, but when I say Moss Landing, I mean the power plant. Moss Landing has a power plant which has a which has some coils. Okay, so Moss Landing is a let's see, I looked up the numbers here. Okay, so basically it's an AC generator, which is what this is, right? This is called an AC signal. This voltage is an AC signal. It's alternating. Moss Landing's an AC generator, and it puts out at the peak voltage is 15.5 kilovolts, and that's generated, of course, at 60 hertz because the frequency is going to match. So as you turn the thing around and around and around and around, whatever frequency you're spinning at is going to be the frequency that the EMF is generated at, and you can see that because the omega in here is the same omega as the one in the other in the flux. Okay, so Moss Landing does that, and I looked up some info on its coils. So it has a coil. So let's take one coil with the diameter, because we need the area, the diameter of 1.25 meters and 60 turns. Yeah. Yeah. Okay. So I thought, I wonder what size magnet they got in there. 1.25 meters. That's a pretty substantial coil. So, okay, there's that. So let's see what field do they require? Oops, is so if I take this thing and I say its maximum value is just going to be this, because the sign's going to maximize out to 1, right? So if I take a look at this and we say, okay, well, what's the B that is needed to make that generator work to kick out 15,000 volts, 15,500 volts? So that means I'm going to take the max EMF, this is now max, and I'm going to divide NA and omega under here. No. Okay, and remember that omega is 2 pi times the frequency. So if I plug these numbers in, 15.5 kilovolts, and we've got 60 turns, an area of pi 1.25 meters squared divided by 4, because it's a diameter. and another 2 pi and another 60. Um, if you calculate all that out, this comes out to something pretty interesting. It's about I got about point 0.6 of a Tesla. Point 0.6 of a Tesla, that's not that big. um, it's not that big, and I think you could probably make that fairly straightforwardly, with, you know, I mean, I doubt it's a permanent magnet, all right? A permanent magnet with a 1.25 diameter, a 1.25 meter diameter iron, no, that's gonna weigh, well, I guess you could. More than likely, however, is it's an electromagnet, and they have they're actually using, well, then that kind of doesn't really jive with producing electricity, but they need something, right? They've got to have lights on, so they have to use some electricity. um, okay, well, so there's the point. I don't really know if that's a permanent magnet or an electromagnet. I guess it would be an but for that size, that would be the only reason I would guess it, for the size. Anyways, so there's a little bit of interestingness. You can take a look at what the Moss Landing plant is doing. Okay. Um, excuse me. I want to go to another thing here. Okay. What I want to talk about now is of no direct consequence. In other words, I'm not going to ask any problems on this, and nor am I going to ask you to know anything mathematical about it, but it's important from a conceptual standpoint. The most important thing that this is going to do is it's going to lead into the next thing. Okay. So this is really just a stepping stone, conceptual link. Okay. And this is what Faraday discovered. He discovered that there was something called mutual inductance. And I showed this in the lab. The mutual inductance is a situation where I have a coil of wire and I've hooked it up to a battery. So let me say that I have a well, I have a coil like this, and it's hooked up to hooked up to an AC source. Okay, so that's what my little sine wave in there means. Okay, coil one. So coil one is something in which the current, and let's back the frequency way down. Let's call it like 5 hertz. Okay, so it's even maybe that, but whatever, doesn't matter. Or 1. Okay, not 60. Don't think of it as 60. That's pretty fast. Think of it as like 1. Okay, my AC source here is a 1 hertz source, which means that the current is initially going clockwise and then counterclockwise and then clockwise and then counterclockwise. And it's repeating once it goes through 1 cycle per second. Okay. So what is that doing? At some point in its cycle, um, the B fields that are generated from the current flowing, right, are going to follow that same thing. So initially, if I have if I have a if I have a clockwise if I have a clockwise current flowing, if I look from the left side and I have a clockwise current flowing, that's a B field going through to the right, and then it reverses and becomes a counterclockwise. That's going a B field to the left. So the B field is going near, near. It's like sloshing back and forth, right? Near, near. Okay. I'm going to run up next to this with another coil. Okay. I'm going to run up next to this with another coil. I'm going to take this coil and I'm going to have a, I don't know, a resistor or something in it, a light bulb. It's not going to be a very interesting light bulb. Okay. Now, from seemingly just having a coil here, that's a bunch of wire hooked up to a resistor, and I can make the light bulb light, right? It's magic through the wireless transmission of power, right? It's really due to the magnetic field changing through coil two's loops, okay? So if you think of the magnetic field that's coming out of coil one, arbitrarily, I'll just pick this at the point where the magnetic field is going to the right. So arbitrarily, I'll just say, okay, here's a magnetic field. Okay, here it goes. I'm not really drawing that very well. Get it out of there. Come on. But undo this. Undo. Undo. Okay, let's try this again. There's some field going kind of, one of them goes like this, and then there's another one that kind of is wrapping around this coil, so it's kind of going a little more like this. Okay. Okay, but there are bits of this field that are making it through the next coil, and they're changing it. Suppose that for some reason I'm picking it, so like I said, going to the right. So there's some flux, and it's changing through the second coil. Okay, and the flux change through the second coil is going to induce voltage in the coil, which, because it's a conductor, makes it a current. Okay, remember the lab, it's not just enough to think of the current that's induced. You have to know that it's a conductor in order for a current to be induced. It always induces a voltage. Even if this was a coil made of wood, there would be a voltage across the wood. Okay, you wouldn't be able to really measure it that well, but there would be a voltage there. Okay. So it's because it's copper wire, supposedly, right, that it's going to generate a current in there. All right. So let's think about the current that's generated in the second coil. Oh, I erased my coil two somehow. Coil two. All right. So there's an EMF generated in coil two. And it's due to changing flux in coil two. The changing flux is due to that changes it changes due to the changing current in coil one. Okay. So can you see what there's a whole bunch of analysis that you could do here. You can go through and look at the field, and then you can go through and look at what fluxes. You look at the field generated by coil one, and then you look at the flux through coil two, and then you look at the d by dt. There's a whole bunch of stuff going on with this. And it's a little bit mathematically nebulous, but hopefully this makes sense. This was one of Faraday's original experiments. He started by putting a coil with a current in it next to a coil with just a voltmeter or a current meter, and found that, oh yeah, look, I can make the needle wiggle because I'm turning this on and off. Okay. So that's wireless power transmission, right? This is known as mutual inductance because I have a one coil inducing something in the next coil. Yeah. So you could write something like E in coil two being something like, I'm just going to say proportional to, something like di1 dt, right? The EMF in coil two is due to the changing current in coil one. If the coil one current is not changing, then I'm not getting a flux change. I'm getting no B field changing in coil 1, no B field flux changing through coil 2. I'm getting a flux, but it's not changing, right? And remember, I got to have something changing. So the uh, the dependence, so hopefully that makes sense. The dependence here is that the voltage in coil 2 depends on the current changing in coil 1, and then there's going to be some factor of a bunch of constants here, right? Which I'm just going to call capital M for mutual inductance, okay? And because because the voltage generated is opposite of it generates a field in coil 2, which is opposite the field, uh, well, it's opposite the flux change in coil 2. Coil 2 generates a voltage, which makes the current in coil 2 flow such that it opposes the flux change through its coil 2. So there's always a little minus in here. So this is the mutual inductance. But the point is that, so this is my segue, right? It's important to know this conceptually because that means you understand that coil 1 makes a B field, coil 2 has an area, and it picks up the flux change through its own area and then responds, and you generate a current in there based on the flux change, which is based on the changing current in coil 1. Okay, so there's that. That's called the mutual inductance, and that requires two coils. However, this is my segue here. There is something called the self-inductance. Okay. In other words, take a look at this circuit. Okay. I'm just going to draw a simple DC circuit here with a switch and a resistor. All right. So here's my delta V of the battery, and here's an R, and here's a switch. Okay. We know that from our analysis of DC circuits that when I close a switch, the battery is going to push current through the wire, and the resistor is going to experience a current flowing through it, and therefore a voltage drop across it. And we're all good with this. It's all an Ohm's rule kind of thing. We can determine the current and all, et cetera, et cetera. But what's new here is thinking about the magnetic flux. Okay. Initially, when the switch is open, there's no current flowing, so there's no magnetic field. No current initially, right? A current in a wire forms a B field, and this is a current loop. This is just a simple circuit, and you can see that the current, when I shut the switch, the current's going to flow in a clockwise manner, which is going to create a field inside there like it's a coil, right? Like it's a solenoid, and it's going to, the current is going like that, and therefore the field's going to go into the page. Okay, no current, so that means no B field. Right now with the switch open. Okay, no B field means no B flux. That's going to change when I shut the switch. Once the switch shuts and the current flows, there's going to be a B field established. Okay, I flows. That creates a B field, which means that I now have some flux through the area of the circuit. Okay, I now have a B field fluxing through the area of the circuit. It was 0, and now it's something. Okay, so that B flux changed. Okay, it changes from 0 to some value, non-zero value. By Faraday's law, that creates an EMF. Oh, that's supposed to say creates. That doesn't look like it says creates. So it creates an EMF in the loop that opposes the flux change. Okay. All right. So here I go. I'm going to close the switch now. Clink. Okay. Switch is closed. Now the current's flowing. Okay. Current. There it goes. We know it's going around like that and around like that, which means that if I circulate with the current, that means I'm getting a B field, which is going to be pointed into the page. Okay. That B field wasn't there, which means it was a zero flux situation, and now it's a non-zero flux situation, meaning that there was a change in the flux during that short time period when I closed the switch and the current started flowing. During that time, there's going to be an EMF generated in this coil because the flux changed through this coil. Note the similarity here, right? Between this situation and the mutual situation. Okay. I closed a switch over here and that caused the other coil to jump. Okay. Now just take away that second coil. If I close the switch in coil 1, it causes a jump in coil 1, right? So I'm just talking about this creating a back EMF in itself, right? So this is a self-induced back EMF essentially, right? And this is how you know that it has to oppose. This is how you know that the generated EMF has to oppose the change. Because at this point, if it was with the change, that means I would shut the switch, the current would start to flow, and then all of a sudden the current would flow a lot more. You think, where'd all this current come from? Not from the battery. No. So that's why it opposes it, right? You can't suddenly create a bunch of current that's like free energy, okay? Doesn't happen. So it opposes the current in the loop here. So what's going to happen is that's the B field from the current that is supposed to be running in the wire. What's going to happen is there's going to be a push back to this, okay? And that means, I guess we're switching to green to do this. So the back push comes in the form of a current which opposes the flux change. So the flux change was 0, and now all of a sudden it's big and into the page. So opposite that would be a B field flux pointing out of the page, right? So this I'm going to call the induced. Well, I'm not. No, I'm going to call it BI, B little I for induced. This is the induced B field. That must mean that the current that's induced is going that way. That's little I. There's a current that runs counter to this, which stops, which prevents the red current from the battery from just going from 0 straight up, right? Prior to this, what we would have expected what we used to expect was, here's the 0 switch on, ding, right? That's what we would have expected before we encountered all this situation at the flux. But what actually happens? What actually happens is there's a push opposing the current. It stops. It says, nope. Okay, so as the current tries to rise, the initial push is usually the biggest, okay? And then as the current slowly gets up to near what it's supposed to be, incidentally, the current value, what you would expect is, of course, delta V over R, right? Delta V of the battery over R. That would be what the maximum current in the coil would be. But what you're finding is it doesn't go straight up to that. It starts when you close the switch. Initially, when you close the switch, that's the biggest flux change, right? That's going to be, the current's going to say, ah, ready to go. It was 0, and now all of a sudden, whoop, big B field, and that causes the biggest pushback. So initially, when you close the switch, it continues to be 0 for a little while, just a little while, and then it starts to rise a little bit. And it eventually goes like that. Okay. So it slowly gets up to that. And of course, when I mean slowly, I mean, you wouldn't observe this just with your eyes, and probably wouldn't observe it easily with an ammeter. It happens pretty quickly, on the scale of what we're used to. But on the scale of what the charges in the circuit are doing, it takes some time to build that whole current up. So at every point, there's a back push from the change. Okay. Of course, you already know, once it gets to that constant value of delta V over R, and the current settles to its steady state, everything shuts off, right? There's no more changing. There's nothing for the induced current to do, so it just goes away, right? There's nothing. Now, on the other side of this, which is when I now open the switch, you might have observed this. Okay, now we open the switch, and instead of, let's actually do this. I'm gonna erase that, extend this a little bit. Okay, so now I'm going to open the switch over here, and dot, 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 dot. Okay, and what you would have expected was that. Okay, current shuts off because there's no connection, right? It's an open circuit once I turn the switch off, right? So this is switch. I should label this also. Switch off. This is switch on. Okay, so when I turn the switch off, of course, you'd expect nothing left. Of course, that's not what happens. Okay, if you've ever, so what happens is the flux was established, and it was this nice value of constant B field going into the page through the circuit that way, and all of a sudden you took it away. So the induced current is going to act to oppose the change of taking it away, which means it tries to push it back up to its original value. Okay, ultimately it does not succeed at doing that, but it is going to try, and it's always going to try. And so what you find is when you turn the switch off, that the current runs a little bit. It runs a little bit longer after you turn the switch off. Okay. So what you find is, and I'm going to change the scale here because I don't want to run into all my nice writing over here. So you're going to find, okay, it goes like that. Which means that current continues to run in the circuit even after the switch is off. And you may have observed something like this. You may have observed a running electrical device trying to keep the current going. When you unplug something that's running from the wall, have you ever seen that spark that jumps? You unplug it and there's a psst, right? That's because you're changing the flux through the current loop, and the current is trying to go, hey, wait, let's keep going, psst, right? And there was some magnetic field energy stored in there, which causes the current to jump. So it continues to push the current a little bit. Okay, so what we have to come up with here, oh boy, this is a long video. Sorry about that. But gosh, this is pretty cool stuff. So what we have to do to show this, okay, what we can do is we can we create a circuit element called an inductor. Okay. It's called the inductor. And the voltage, that's what I should also have said too. I forgot to do that in the self part. The like with the mutual inductance, the voltage generated, the back EMF, I'm going to say the back EMF generated in the loop, or that's what I called little I, the induced one, is proportional, therefore, like it was before with the mutual inductance, right? It's proportional to the rate of change of the current. There's some M times di dt. Well, in this case, it's going to be proportional to something like an L di dt. But in this case, the di dt is because of its own current, not the current in something else. It's its own current. Its own current causes a back EMF. Okay, so that's the in analogy to the mutual inductance, right? So the circuit itself feels a voltage pushing the other way due to the di dt in itself. And this thing here is called the self-inductance. And we just eliminate the self and we just call it the inductance. So each circuit has its inductance. There's an inductance in it. We just don't, we don't say it's self because it's in itself. Okay, so there's a circuit element called an inductor. So let me redraw this circuit here. Okay, and now we have an inductor in the circuit. Okay, now that's going to be the thing that you like. What am I trying to say here? When you think of resistanceless wires, okay, there's obviously no such thing. But what you can do is you can take a small resistor and just put that into the circuit. Okay, this resistor R here is for all the resistance of all the wires, and then you can make all the wires resistanceless. Okay, so you can model wires with no resistance by just adding a little resistor into the circuit. Say, that's part of R. Part of R is the resistance for the wires. That's the resistance of the whole circuit. Now I'm going to make this inductor the inductance for the whole circuit. So it's going to be the thing that takes care of this problem. I don't have to worry about it. So I shut the switch, right? There's no current flowing, and then I shut the switch. And the inductor goes, "What are you doing? Stop!" And it kicks a back EMF up, which prevents the current from just jumping up, right? Because look at this red line up here. If I took a look at this and I said, what's the slope of that line right there? It's infinity, right? It changes. It's a step function, right? It starts at this and then it goes to this and it does it. It's like infinite slope. Of course, you can't have that. So, so the inductor responds to a di dt in the circuit. So when I shut the switch, that's a big di dt, because before that there was zero current, and now there's trying to be some current. And I'm saying, if I'm the inductor, I'm saying, stop. Okay. Okay. However, once the current starts building up and reaches its steady state value, okay, so now I'm going to say, all right, switch is closed. Boop. Okay. There's current running through the circuit, and it's delta V, delta V over R and all that stuff. Okay, but look at what's happening. So I modeled this inductor as a coil. Okay, so I looked at it as a coil. And so if I'm thinking of current running through a coil, then what's happening is I'm getting a B field through this coil. Okay, so there's a B field here. Let's say it's going that way. There's a B field in the coil. And when the current is at steady state, that's a constant B field. So you're going to see that the B field is present and not doing anything. But then, because you might ask, how does the current keep going after the switch is shut off, right? How does the current keep going? Well, there's energy stored in the B field that's in the inductor. Yeah. So that I did work to build the B field up. Now that it's established and it's there, when I undo the switch, the B field says, oh, I still have energy stored in me. I'm going to continue to push current. Okay. So that's where the energy stored up. It's the essentially, it's the magnetic equivalent of a capacitor. Okay. Um, B field builds up at steady current. Okay. So the B field comes up at a steady current flow and it just sits there, right? Just as if a capacitor had an E field sitting there, right? You could charge the capacitor up and then you'd have an electric field there. And then you could discharge the capacitor through a light bulb and you'd see the light bulb come on because you stored energy in the capacitor in the electric field of it, right? Well, the same thing's true here. The B field builds up at steady current flow. There is energy stored in the B field. Okay, there's energy stored in the B field. So when you undo the switch, it keeps driving current through the circuit just for a little while, as best it can. And it certainly it goes out quickly, usually, right? But it'll discharge itself. It's not really a very good word because there's no charge, but it'll disenergize itself. It'll release its energy. I don't know quite how to say that. Energy stored in the B field, and it can come out when switch is opened. Okay, it drives the current for just that bit extra time. All right, so this is the inductor, and the voltage across the inductor, let's do it this way. Let's say delta V across L is in fact exactly what we thought it was up above. It depends on the rate of change of the current. So it only kicks when there's a rate of change of the current. And if there's no rate of change of current, then it just acts like a piece of wire. And the piece of wire the current just flows through it. It just so happens that it's wrapped around and is coiled. Therefore, there's actually a B field in the wire. And so that when you try to then open the switch, that's when the DIDT starts. And then it tries to supply the current to keep the flux the same. Okay. So that's a circuit element known as the inductor. It is an energy storage device in the same way that a capacitor is. Okay. A capacitor ultimately stops the current flow, but the inductor ultimately tries to inhibit the start of the current flow, right? So they act kind of oppositely in that sense. All right, so I'm gonna call this I need a stop for now. I'm sure you do too. Next one, we'll talk a little bit more about some uses of the inductor, maybe do one more flux example, and then we'll start looking at some DC behavior of the inductor. And then next week, we'll move into some AC behavior of both inductors and capacitors. All right. Happy rest of your day, friends.